Santiago from Kempfog to status updates on Rocket and its integration with Kubernetes.
Thank you. So yeah, hi, how are you? Thanks, Stefan. I'm going to talk about Rocket. It's basically a project status update, so what's being new or relatively new in Rocket, and also about its Kubernetes integration, which is Rocket-Lit. So first, something about me. So I live in Berlin, which I really like, so it's first on the list. And I'm one of the co-founders of Teamfold. So at Teamfold, what we do is we're basically a software team that companies hire us to do development on their products, and we help their teams with that. And we did a lot of work on Rocket with CoreOS, and then on Rocket-Lit after that. And I'm currently a maintainer of Rocket and Rocket-Lit, and you can see my GitHub there and my career. I don't really tweet much, but I retweet a lot. So the plan for today is I'll explain a bit what is Rocket. I assume that most of you will have heard about Rocket, so I will keep it brief. And I will explain a bit how Rocket works, some interesting internal details. Then I will do the same with Rocket-Lit, what is Rocket-Lit, how does it work. And then I will talk about what's new, and then what's missing, so future work. So Rocket is basically, that's the tagline, a modern, secure, composable container runtime. And we say modern because we try to take advantage of the latest technologies in Linux kernel. We say secure because we try to make it secure by default. So by default, everything is locked down, and if you want to disable stuff, you have to do it explicitly. And composable because we try to play nice with the rest of the system. We try to reuse components that are already there. So basically, Rocket is an implementation of the AppC spec, which is now not really actively developed, but I think it kind of triggered future movements like the OCI spec and all that stuff, all this standardization that happened in containers. The AppC is an open specification. It defines some concepts like the image distribution and things like that, and it has some associated tooling. So there's a lot of things in the AppC organization of GitHub. But basically it defines 4 things: the image format, which is the ACI image format, and that defines what the application consists of. So basically a container is just a tarball with some associated metadata that's usually a manifest, and that defines how this tarball should be executed, like which namespaces, what security features should be enabled and stuff. So that's the image format. The AppC also defines the image discovery, and this is how you can go from an image name to an image artifact, so this tarball I was talking about. And that's pretty cool because it reuses the DNS system. So if you have if your container is named corporation.com/whatever, it will go to that website, and then that website will have some metadata that will tell you where the actual artifact is. And that's cool because it's distributed, there's no centralized registry, and so on. And so it defines the concept of pods. So in Rocket, containers can be grouped where it makes sense. So if a container needs access to some other container, it makes sense that they're all lived together. So the pods define that concept. It's very similar to the Kubernetes pods. And then the executor, this is just what the application should expect when it's running. So the environment it runs in. So in the end, Rocket is just a CLI tool. It doesn't have any daemons. It's just a CLI tool that you run, and then your container is running. It's written in Golang, and it's Linux specific, so we don't try to support FreeBSD or macOS or all this stuff. It's pretty self-contained, so it just has some simple dependencies to DLC and the typical dynamic libraries you have in your Linux system. And it's in its system and distro agnostic, although we optimize this to run on their system D. So this is basically the typical tree diagram of Rocket. So something will start Rocket, might be systemd, might be bash, might be our unit, you name it. And then Rocket will start a pod. So you see there's 3 stages: stage 0, stage 1, stage 2. So stage 0 is just a Rocket binary CLI, so that does image fetching. It renders the image in the file system. Stage 1 is the actual container, so it's the environment that pods will live in. And it does process lifecycle management, and it contains the resources. And in stage 2 is just your application, so it's whatever you run. One cool thing about the stage 1 is that it's swappable, so there's different implementations. The default one uses unit namespaces and C groups, which is what people used to call the Linux container. And it's based on systemd and spawn, and inside that container, we run systemd again to manage all the applications in the pod. There's also different implementations. There's KVM implementation, which it uses hardware virtualization instead of Linux containers, and it's based currently on QEMU and systemd. So that's very cool if you have a full VM where you can run your applications. And then there's Fly, which is something that has no isolation, it's just a CH root. And it's there because to take advantage of Rocket's image distribution mechanism, that helps when you want to run just an application without isolation. Okay, so now I'm going to talk about a bit about Kubernetes. So probably most of you will know this, but I will give the introduction. So Kubernetes is just an orchestration system, and it provides the developer with an API, and the developer can just submit containers to that API and doesn't have to care where those containers will run and which nodes. And the thing I want to focus here is this kubelet thing. So this is a component that runs on each node of a Kubernetes cluster, and it's the one that's actually tasked to execute the containers themselves. So in the beginning in Kubernetes, everything was Docker, and that was not ideal. So when we tried to put Rocket in Kubernetes, we discovered all these assumptions in Kubernetes that were there, and that led to the creation of the CRI interface. And thanks to the CRI interface, now we have different implementations for container runtimes in Kubernetes, like Cryo, like CRI containerd, or like Rocket, which is what I'm going to talk about next. So the CRI defines some interface that container runtimes need to implement, and these methods like run pod sandbox to create a sandbox that's empty, no containers there. Then you can add containers, and you can then start containers and stop containers. So basically an interface that abstracts away the container operations. And then the kubelet calls these methods via gRPC, and then you have something on the other side of the gRPC connection that implements that. And as I mentioned before, CRI containerd is an example, Cryo, and Rocket. So how does Rocket work? As I said before, the kubelet is there. It sends a gRPC request to the Rocket daemon, and then what the Rocket daemon does is it will start a systemd unit per pod, and then it will add and remove containers if the operations require that, communicating with the Rockets running as systemd units. So it's pretty simple, and then you take advantage of systemd's supervision capabilities. So to implement the Rocket we had to do some design changes to Rocket, because on Rocket we had this concept of immutable pods. So your pod is defined from the beginning, and then you just run it. But the CRI defines something different, influenced by the way Docker works, because in Docker there's no pod concept, so you just have containers and then they're linked together. So we had to implement mutable pods in Rocket. And to do that, we did this, what we call the app experiment. And basically we had an install command for Rocket that creates sandbox, and then we added more commands to add containers and remove containers and start containers and stop containers. Since, as I said before, we're running systemd inside a container, this was pretty easy because this maps pretty well with systemd concepts like create a new unit file, or remove the unit file, or start a unit file, or stop the unit file. So that helps us. And for now it lives under a variable, so it's not really visible by default. And that's the name of the variable. Another problem we had was logs. So Rocket used journal-D inside the container to manage all the logs. And the CRI doesn't really like the binary format of journal-D, of course. And this very wants text format, like plain text, very simple. So the initial solution we came up with was kind of a hack, because we just add a sidecar app to the pod, and that app will translate the journal logs to the CRI logs and write it in the right place. But that's kind of that was kind of unreliable and resource consuming. For example, the image was, I don't know, 500 megs, which is not very ideal. So the proper solution is we did this experiment attach, and it's basically creating this component called IOTT-WiMAX that sits in the middle between the outside of the container and the application, and just intercepts all the standard output and error and input of the application, and it can write the output and the error to the file directly without having any translation. So this is the diagram of how it works. So you have your structure there, and you have system inside the container that starts the IOTT-WiMAX component, and then the output of the application is connected to IOTT-WiMAX, and that's being written to that file there. And yeah, that's a simplified version of the format for the CRI logs. It's just a date, the stream type, and then the log line. And this will also allows us to attach to the input and output of the application, which was not possible before. So yeah, it allows us to implement something like Rocket Attach. So yeah, those were the most difficult parts when we tried to integrate Rocket with Kubernetes. So now I will talk about the recent developments in Rocket. Yeah, so this is some kind of a random collection of new things that happen in Rocket. So we implemented the sharing IPC namespace because, as I said before, Rocket uses nspawn, and nspawn doesn't have a concept of only share this namespace, only share that namespace. It does all the namespaces, well, except the net namespace if you opt out. So what we did basically was add some hidden variables to systemd nspawn, so we can actually share namespaces independently from each other. So yeah, and then we implemented the Rocket part, and this was done for some high performance computing client that needed the IPC namespace to be shared between containers. Yeah, we did a lot of fixes in Rocket to make Rocket-led possible. A lot of bug fixes on the Rocket experiment I mentioned before. And we added integration between this attach experiment, the IOTT-WiMAX component, and Kubernetes. And also we switched the default KVM flavor from LKVM to QEMU, and that was because LKVM was kind of unreliable and it had some problems with mounts. So QEMU is much better in that regard. Yeah, and recent development that happened was documentation. So documentation is important. And thanks to the CNCF that funded us to actually write a bunch of documentation. And you can see there that we closed 31 issues after November of last year. So that was quite a lot of work. And yeah, we think the documentation state of Rocket is pretty nice now. And we added also some documentation to Rocket, which was lucky. Okay, so what comes next for Rocket? We need to update the CNI version because Rocket is using version 03, and some features were added later that people are interested in. So this is something we need to do, but it's kind of hard because yeah, there's a lot of assumptions in Rocket that depend on the previous behavior of CNI. We should stabilize the Rocket experiments because yeah, it's not nice having to add an env variable there to do this sandbox kind of thing. So we should just remove them and make sure they work fine. There was some experimentation of using runc to set up stage 2. And this is so because what we've been doing now to start applications in a pod is run them in a systemd unit file, which has a lot of primitives like seccomp. You can enable non-new privileges. You can enable all kinds of stuff. So usually they translate well with the CRI specification, but sometimes some things are slightly different, so that's kind of hard. So the idea is to use runc, which is defined by the OCI. So using runc, we will have basically the same options as other runtimes. one cool thing that my colleague Alban was experimenting with is using CA-Sync. I'm not sure everybody's familiar with CA-Sync, but it's basically rsync plus content addressable, and it makes you, it's a very efficient way to transmit images. And there's a talk later today by my colleague Alban at 3 p.m. I think it is, and if you want to know more about that, please attend that talk. So there's, right now Rocket has OCI image support, but it's not ideal because it's basically integrated in the Docker support of Rocket. So what we do basically is we take the OCI image from the Docker registry and then we convert it to ACI, and then we run it in Rocket. But thanks. But there's a possibility of doing it natively, so you don't have to do this conversion step. And of course, general bug fixing, because there's always bugs. So you're talking about the CA-Sync tests. There's some graphs there. So the red thing is the amount of data transmitted using CA-Sync, and the blue thing is the amount of data transmitted without using CA-Sync. But as I said, there's going to be a talk on this, so you'll get more details there. So what comes next for Rocket Lib? So we don't fully support SCRI. There's some things missing, and the most important things are QCTL attach and port forward. That doesn't work at the moment, although IFTTY maps allows us to do that, but we have to write the code for Rocket. The CRI container stats is a new interface where the kubelet can ask for stats to container runtime, so instead of doing CAdvisor and checking the C groups manually, it's kind of ugly. That's not implemented there. And we should improve performance because we've just been focusing on making it run, and we haven't really looked at the performance yet. So we run the end-to-end performance tests in Kubernetes, and we don't pass them all. So currently we passed 130 and we failed 15. Some failures are kind of easy to fix. Some failures are not so easy. But yeah, as I said, I work at KeepTalk, and we're a consultancy, so we cannot just work on this unless we have a client that requires us that pays us to do this work. So yeah. And yeah, I had a demo. Oh, the markdown is kind of screwed up here. But the demo is also screwed up, so sorry. The demo was a Kubernetes cluster using Rocket Lib and running on kubectl, which is a tool we built to run clusters that don't run on VMs. That run clusters on your local machine that don't run on VMs, but run on containers. But the connection here is kind of shitty, and I have to download things, so that didn't work. I have 1.5 minutes for questions.
Any questions? Yeah.
Well, my question is, can you make the KVM and default runtimes at the same time? Like, split some containers virtualization?
Yes, you can. It's just a runtime option, so you can just run in parallel everything.
Any other questions?
Okay. Thank you.